Thank you for the introduction. Good afternoon, everyone. It was great to see many of you at our demo. I'm Yoshiki from Kitamura Lab at Tohoku University, Japan. So today, I'd like to talk about our research project, AdapTable. In this project, we explore how to extend reach over large tabletops through flexible multi-display configuration. In everyday life, we are all familiar with various kinds of workspaces. For instance, connected table, group table, individual places, or a combination of these. Besides individual work, we also give presentations, organizing meetings, or engaging group work. With many activities taking place within short time, so how should our work environment be designed to switch efficiently between activities? Surely, one approach would be to have dedicated rooms for each activity. However, we believe there is a growing need for reconfigure workspace. So many researchers have presented a way to achieve reconfigure workspace. Transform table can automatically achieve tabletop shape shifting. Users do not have to move or change the tables for different situations. It provides an appropriate configuration according to number of users and their spatial behavior. Living desktop can automatically change display, keyboard, and mouse position based on user behavior. Shape-shifting wall displays can automatically change display's position and orientation based on content and user position. So today, we focus on a flexible multi-display large tabletop that can physically reconfigure its layout. Interactive tabletops comes with a few characteristics offering certain benefits. They offer interactive horizontal display and serve as strong communication enablers. Therefore, they are often used in places such as office and classrooms. For larger workspaces, you can find tabletops ranging from 50 to 65-inch size for individuals and groups. In special cases, such as museum or control centers, you can find a tabletop exceeding 100 inches for a larger group. So such large tables can provide vast workspaces, and users can potentially work more efficiently and comfortably. However, it is not clear how benefit increases with size. Large tabletops have a content access issue. That is, when users want to reach distant objects, they may be forced into an unnatural posture or need to move around the tables. Following previous research, they can only employ a limited reach area, here shown in red. So most of the time, users do not benefit from the entire display and cannot comfortably manipulate remote objects, which is a problem we address today. Remote object manipulation has been proposed as one way to overcome the issue of reach. iGrab allows the user to select and move distant content. The user can use the technique by touch gesture. Pointable allows the user to manipulate content through a pointer, which is controlled by the user's mid gesture. Using these techniques, users can manipulate distant content, but this technique does not efficiently support complex interaction. Panning is a more established way to interact with remote objects. Users can easily bring content closer, but can also lose content. This may cause repetitive movements, sometimes called clutching. In contrast to these techniques, our proposal brings a user closer to the content. We propose AdapTable. It's a flexible multi-display tabletop that can physically reconfigure its layout and allows for interaction with difficult-to-reach regions directly. Users can easily make use of flexible layout depending on the current task. This video shows a few typical layouts. In this research, first, we conducted a layout design study to find users' preferred table layouts for full-screen interaction. We then prototyped AdapTable. Based on this, we conducted a user study to evaluate the AdapTable system. In the layout design study, we explored the questions. Depending on scenario and the task category, will users make use of flexible layout? If yes, which layout do they prefer? How do the layouts affect task performance? To investigate the questions, we prepared 7 target distribution scenarios, 2 tasks, and 2 layout conditions. We used a within group design, and we recruited 14 participants. The right image represents 7 target distribution scenarios. The green areas offer more interaction, and the yellow area offers less interaction. Here, we see the reaching task. Participants were instructed to select the red object as fast as possible. In the merged condition, participants couldn't change the table layout during the task. In the flexible condition, participants could change the table layout. To the right, we see the docking task. Participants were instructed to translate and scale the red object by using touch, drag, and pinch motions to place it on the target squares. The docking task is more complex and difficult than reaching task. During the tasks, participants could walk in front of the tables and create a new space by changing table layout. For multi-display tabletops, we prepared 4 27-inch multi-touch displays horizontally mounted on cards with casters connected to a desktop PC. Participants could easily move each of the tables. From the tasks, we found that participants prefer to change table layout. More than half of participants change the table layout on the 5 layout. From here, we consider the result from the 5 scenarios. For each task, we counted how many times each layout was chosen and show the top 3 candidates. Here is the percentage of all choices. Participants reported they changed the layout to access distant contents more easily. They found that slide layouts were good to achieve more equal reach per screen, and that single slide does the job with a smaller change. Finally, they told that the split layout keeps the content vertically aligned. In addition, we learned that participant experience reduced physical demand by changing the table layout. For the docking task, they also reported lowered frustration. Through the layout design study, we learned that users prefer to change table layouts and could work more comfortably and efficiently. As a next step, we prototyped AdapTable with 5 layouts. To prototype AdapTable, we used the same multi-display tabletop from the layout design study and mounted each table on a Roomba to move the tables. Each table and user was tracked by a motion tracking system. For controlling the AdapTable, we implemented 3 interfaces. The first one was touch menu. By selecting an image which represents layout, a user could change the layout. The second one was touch gesture. Users could change the layout by swiping their fingers on the display. The final one was user position. Unlike touch menu and touch gesture, this system automatically changes the layout based on user position. From the informal user study, we found that users prefer the touch menu. They reported it was easier to use and required less memorization. Hence, we chose touch menu for the AdapTable system implementation. Finally, we conducted a comparative evaluation where we compared the panning with AdapTable by task completion time and NASA TLX. For the study, we prepared a 5 target distribution scenario, 2 tasks, and 2 interaction technique. We used a within group design, and we recruited 20 participants. Here we see the flag task. In this task, participants were instructed to translate and scale each flag by using touch, drag, and pitch motions to place it on the target scale of the corresponding country. In adaptable situation, participants could change the table layout any number of times. In panning situation, participants could move the content by swiping 2 fingers anytime. To the right, we see the number task. Again, participants were instructed to translate and scale each red square by using touch, drag, and pitch motions to place it on the corresponding target square, showing the same number. The difference between the flag task and the number task was the cost of visual search. In the flag task, we displayed a world map as a background, so participants would know where to place each flag. In number task, the background was white, so there was no information. Through these tasks, we found that AdapTable could significantly reduce task completion time compared with panning in the large and left vertical scenarios. For NASA TLX, AdapTable significantly reduced frustration compared with panning in the number task, since with panning, participants sometimes lost content and needed to retrieve or remember it. Okay, so let's move on to discussion. In summary, AdapTable offers its users to keep all content visible, and it also enables full-screen interaction. However, there are still open issues that call for further research and engineering. By moving the tables and bezels around the screen, the content is divided. To build a more flexible workspace, we think workspace personalization is important. In AdapTable, we used fewer predefined layouts, but it would be beneficial if users can customize the menu according to their preference. The AdapTable prototype can switch its layout in 2 seconds. We set the speed to switch quickly and safely. Yet, participants sometimes felt this was too slow, so it would be helpful if the user could customize the speed of the automated reconfiguration. In this research, we explored large tabletops with 4 tables, but we think our idea can be used more or fewer tabletops to build a more dynamic and adaptive workspace for a different situation. Our prototype can change layout horizontally, but to build a more flexible, reconfigurable workspace, it would be helpful if the user could adjust the height of the tables. Of course, this concept can work for collaboration. For example, a user could change the layout based on content or move the table for communication. So what did we learn through this work? First, we conducted a layout design study where we found users prefer to change table layouts for full-screen interaction. We then prototyped AdapTable using 4 actuated tabletop display, each propelled by a mobile robot, and a touch menu was chosen to control the layout. Finally, we conducted a comparative evaluation and found that AdapTable provides a more efficient method for complex full-screen interaction in some scenario. Thank you for your attention.
Do we have any questions for our speaker?
Yeah, Raimund Axel, Interactive Media Lab Dresden. Thanks a lot. This is very inspiring and interesting work. I also enjoyed the demo, and unfortunately, it doesn't clean at the same time. So the Roomba robots do not clean the ground at the same time while you're using that. I just wanted to make a comment. Actually, I didn't want to ask a question. I just wanted to comment on that because this paper is somehow really nicely reflecting our name change from the ITS to ISS. This one because it picks up the idea of course, extending the tabletops to a more movable, into space basically, changing architecture to changing display. So I like this idea of extending this just flat and stiff surfaces to more flexible displays or interaction surfaces which extend in our physical space. So congratulations on that you picked up the name change very well in this paper.
Thank you.
I had one question.
Johannes Schöning, University of Bremen. Thanks for this nice presentation. Maybe I have the question regarding Raymond's comment. I was wondering, especially when you showed the video in the end, where you showed the scenario with the 8x8 or
the 16 or more.
Or 16,
or
whatever
more,
display. You need some space, and I was thinking you need some space to move them around. And typically, and your rooms in the renderings were completely empty. And if I think of situations rooms or boardrooms or discussion or meeting rooms, space is limited, and you're maybe not able to move the displays around as freely as possible. Have you considered the additional space you need for moving them around? Probably. Is there like a restriction? Have you thought about that? Because if not, I think that's a very interesting point for future work, that you also have the additional space to provide those transformation of those displays.
Thank you for the question. Yeah, so thus, if there are no space to move the table, this system is not good. But we are thinking, so we have space around the table, and if we don't move the table, use a move around the table to interact with distant objects. But instead of that, by moving a table, we provide additional other space into the table. And so this is for the our system comment. But so to build a more flexible the workspace by controlling whole system, I think we need to think about not only table but also wall or other physical space to manage. So yeah.
Hi, my name is Rucha. I wanted to ask again about the last animation you showed. Have you thought about this one, not this one, where there are multi people involved in this?
So this one?
Yeah, like this. So if there are multi interactions within the user interface, then how this will work? Have you? Is this a future work, or you're working?
Yeah, so in this research, we focused on a single user. Okay. So yeah, the collaboration is our next step. Mm-hmm. But yeah, to build the adaptive workspace for the multiple people, we need to think about how to control the tables, or right, how to manage their workspace for each user. Yeah. Yeah,
or will it look like a puzzle or something, like? Whereas, 2-3 people are interacting with the table, and the table is moving from, various areas. That I can think about it.
Sorry.
So I'm thinking, like, if there are 2-3 interactions going on, and if the table is understanding 2-3 interactions and moving, wouldn't it look like a puzzle or something? Like, it will, yeah, it will break into pieces and then come again, and something like that. Some sort of that sort of interaction will happen. This is what I'm feeling. It's not a question, it's just a comment. Don't worry. Thanks. Thank you.
Thank you. One last hand for